So we will continue our discussion on canonical problems in distributed systems. Last time I described this notion of a logical clock and vector clocks. So the key takeaway there was, since clock synchronization can never be perfect, there is no global clock. If you want to reason about events and which one happened before which other event, you can simply use local events within a process to order events locally, and you can use message exchange to order events across processes. And we saw a timestamping algorithm that allowed us to achieve that property. Okay? And remember what I said was Lamport's clock allows you to take events that have an ordering defined on them in terms of happened before and assigns timestamps such that the clock values are in the order of the events. If you want to just look at the timestamp and infer the ordering of events, you need vector clocks, which give you the implication in both directions. Logical clock gives you the forward implication but not the reverse. The clock values are ordered, it doesn't allow you to say anything about ordering of events, but vector clocks do. Okay, so we basically talked about logical clocks, vector clocks, and towards the end of the class I was talking about distributed snapshots. So just to recap, if you want to capture the state of any distributed set of processes, or what is referred to as a distributed system or computation, you want to checkpoint the memory state of each process and capture all the messages in transit. So if you restart the application from that point on, it will compute forward in a consistent fashion. Okay. I defined this notion of a consistent cut and an inconsistent cut. A consistent cut is one which allows the computation to start in a consistent way. And the main issue in the consistent cut is you do not have a scenario where messages are missed or messages have been received that haven't yet been sent from a perspective of the cut, which will cause duplicate messages. So we said, how do you design an algorithm to implement a consistent cut? And that's where we talked about this notion of distributed snapshot. So I'm going to recap the algorithm, have a brief discussion of why it works. Okay, so the algorithm is such that any process in the set of n processes can initiate a snapshot. Multiple snapshots could be in progress at any time. So we will have a snapshot ID attached to a snapshot. So when you send messages, you will say, take a snapshot, and this is snapshot number X. So snapshots can be distinguished from one another. Okay. So the algorithm is as follows. Any process can initiate it. The way you start the algorithm is you first take your memory state, you write it out to disk. That is referred to as a local checkpoint. Okay. So think of it as a core. Just as when you have a core dump, your entire memory state goes to disk. You take everything that you have for the process in memory, you write it out to disk. Okay. And then you send a checkpoint on every outgoing channel. Okay. And you start recording all the messages that are coming on your incoming channel. Okay. And this process is going to continue recursively. Whenever any of the processes now receive this marker message, a marker message is essentially a special message that says take a checkpoint. Then if you receive the first marker message for this snapshot, you take your local memory state, you write it out to disk. You repeat, you send out marker messages on all outgoing channels. You start recording all incoming channels. What do you mean by recording is every message that arrives on a socket, you write a copy of that message to disk. Because these are messages that are supposed to be in transit. They have been received but not yet been processed. Okay? And then when do you stop recording on an incoming channel? You stop recording when you receive a marker message on an incoming channel. Okay? So you send one on the outgoing channel to tell all your neighbors to take a snapshot, and you start recording, and you stop recording when you receive a marker from that neighbor back to you. Okay? So this is the distributed snapshot algorithm. And at the end of, so first of all, we will describe why this process even terminates. But assuming it terminates, what has happened is every process has taken a snapshot of its memory state, a checkpoint of its memory state. It has recorded all of the markers, or rather not markers, messages that are being received from all its neighbors. Okay, also to this. So your disk state will involve your memory state and a copy of all of your messages. There's a picture somewhere here. which basically shows what's going on. So here is process Q. So it sends out marker messages on its outgoing channel. This gray thing is its memory state, its copy of its memory. That's its incoming channel. There should be one for each outgoing, only one is shown. So every message that is coming in on that incoming message is also stored on disk. So you have A, B, C, and D stored on disk. And then once you receive a marker message that says stop recording, the first marker says start recording. The last the incoming markers on each channel say stop recording. That's the meaning of what a marker is. So it's basically you record everything between the start recording marker and the stop recording markers on your incoming channels. Yeah, so that's basically what is saved. So for this process, the recorded state is that gray box is its memory state and 4 messages that came in that were in transit A, B, C, and D. Okay. Every process is going to do this, and then you will basically get a snapshot. Okay. So now we have to ask 2 questions. First of all, since all these markers are going back and forth, will it cause the algorithm to actually finish? Okay. There shouldn't be any loops that cause you to keep on recording either messages or taking snapshots and so on. And the second is that we have to have some sort of an argument as to why this is a consistent cut. Why is this a consistent snapshot? Why have you done the right thing here? Okay. So let's start with the first problem. Okay, will this algorithm terminate, which means will it finish? Will every process eventually stop recording? Assume that there are no failures or anything like that. Okay, so we are not describing a scenario where processes will crash or some such thing. Assuming all the processes are operating normally, will a distributed snapshot algorithm terminate?
Yes.
Yes. Did you say yes?
I didn't, but I think yes.
Okay. Somebody said yes. Who said? You said yes? Okay. So can you give some sort of an argument as to why it may terminate?
Well, it'll always terminate when it receives the second marker, right?
Yeah.
So as long as there's no failures, then we'll receive the marker and we'll stop.
So point being made is if you receive the second marker, you will stop, and we have to argue that you will actually receive a second marker. That will cause you to stop. So let's take 2 processes, a system with 2 processes. Let's see how it works. Okay. So they have a TCP connection. It's a duplex. All TCP connections are typically duplex. So there's an incoming and an outgoing channel. Process A, process B. Okay. Process A, let's say, starts the snapshot process and says take a snapshot. So it's going to take its memory state, write it out to disk. Okay, that's the start. And then it is going to send a marker message. Okay. And then it will start recording all the messages that are coming in from B. Okay. So now what happens at B? So each of these messages is being recorded. Now B is going to receive this marker message. That's the first time it's seen that says start recording. Okay. So B is going to write out its state to disk. And what does it do? It's going to send a marker on its outgoing channel, which is, there's only one, so it's going to send it that way. Okay. So now from A's perspective, eventually a marker will show up, right? Because for every outgoing channel you send, and then when that process receives your marker, it's going to send one back in the opposite direction. So then for that channel, clearly you will basically, this will tell it to stop recording. So you have these 4 messages, and then it is going to stop recording. So A is going to stop. Okay. What about B? A is going to again send a marker to B. Okay. If you send another marker, this process will not terminate because it will go to B. B will send you a marker back and so on. So you just sit in a loop. So when does B stop recording? Okay, so suggestion being made is when A receives this marker, it's going to resend a marker, and that will cause B to stop recording. Anybody else have any thoughts on this?
It has to be able to distinguish between what markers, right? Because like I said, you always go and try to But I don't know that the record is like.
So first we have to see what did we say the algorithm is, right? So on receiving a marker, if it's the first marker, you're going to send on the outgoing channel and save messages. Okay. Subsequent marker on a channel, stop saving state for that channel. That's basically what we have said. Okay, so now this actually is turns out to be a special case. B does not need to receive a second marker, okay? Because it has already received a marker on its incoming channel. That was the very first marker to begin with. Okay, when the first time you receive a marker on any incoming channel, that not only tells you start recording, it also tells you stop recording. Because so on that channel, the only thing that you're going to record is your local state. There is no messages to record. Because every marker on your incoming channel is going to tell you to stop recording. Okay? The first marker also tells you to start recording. So on this incoming channel, this first marker that was sent from A to B not only told B to start recording, it also said stop recording. Because by definition, we said when you receive a marker on your incoming channel, you stop. So there was nothing to record other than your local memory state as far as this channel is concerned. Now, if B itself was actually talking to C, this first marker would have caused it to send a marker out to C, and then it would have recorded everything that is coming from C, and when that marker came back, it would stop recording on that channel. Okay. So for all subsequent channel, you will actually receive another marker message subsequently. But the first time you receive a marker message, and since that's an incoming channel, clearly it's going to tell you to do both things, start and stop. So if there are only two processes here, B has nothing to do other than it processed the marker already. It has already received it. That was the very first one. Okay. A, on the other hand, will send something out and will wait for something to come back on its incoming channel. So it will record. Okay. So there are 2 points. One was a subtle point which said that the first time you receive a marker, it actually means both things, start and stop at the same time, because it's a marker on the incoming message. The second point we were trying to see is this algorithm going to finish? Okay, the point that somebody made was, if it's a duplex TCP connection, if I receive a marker, I'm a process, I send it out on the outgoing, and that marker goes to that process, it should send something back. So basically then you will always get something back and you will stop recording. This will happen for every TCP connection. You will send something, you'll get something back from that process. So you will eventually receive all markers on all your incoming channels, so you will stop. Okay, so if you send something out, you should get something back. Okay, so every process is going to see the same thing. Okay, so eventually every process will stop. Okay, so the algorithm is not going to go into some sort of an infinite loop. You always send only one marker on your outgoing channel, you always receive only one on your incoming. You don't keep sending, okay, for one snapshot. Okay, is that clear? Yes or no? A somewhat subtle point.
How does this ensure that this algorithm will help to make us consistent cuts?
Okay, so the second question which we have not discussed is, why is this algorithm giving you something? It's an algorithm doing something. It's recording memory, it's recording messages, but is it actually giving us a consistent cut? That we have not yet described as to why it is actually doing the right thing. Okay, but first question was, is everybody convinced this algorithm will actually finish at some point in time? Okay, if that is yes, then we'll ask the more difficult question saying, is this algorithm of any use? Is it doing something that we care about?
How the A is connected to C?
Okay, so there's another question. So what is A if A is connected to C? We can do the same analysis. Okay, here, in fact, that is actually the picture here somewhere. Which is that picture there. Okay, so if A initiated the snapshot, you can ask what is going to happen, right? So A takes a copy of its memory state, it sends markers on all its outgoing channels. Now there are two outgoing channels in this scenario, B and C. So it's going to send a marker to C, it's going to send a marker to B, and it will start recording whatever is coming from C, is going to start recording whatever is coming from B. Okay, so now C and B are going to eventually receive these marker messages and send marker messages back. So that part is still going to happen. But in addition, what's going to happen is B may send a mark, depending on who receives it first. B may send the marker to C first, or C may send the marker to B. It depends on who is closer and who processes the marker faster. But one of them will receive the marker first and send the marker off to the other entity. Okay? So now each of these will receive. So A has already sent the marker. So B and C both know that the snapshot is in progress. So when a marker, so let's say B receives it first. Let's take that case. Okay? So B sends off a marker to C. Okay? Now when C has already received a marker from A, and it is actually also going to send a marker on its outgoing channels, which is going to send one to C. Okay? So when it receives this marker, it's no longer the first marker because it's already received one from C. So this marker is merely going to cause it to stop recording. There's nothing else to do because the first marker from C said this snapshot is already in progress, so start recording. Okay? So there are two ways you can receive a marker on an incoming channel. If you sent a marker and that process sent it back, or before you even send the marker, some other process has sent a marker to that process and it sent it to you because its outgoing channel is your incoming channel. Okay? So in either case, it is going to work fine. It just depends on the timing. And it doesn't matter which marker is received first. The first marker causes you to checkpoint. Start recording on incoming channel, send markers on outgoing channel. So it should always work regardless of which order or what speed things happen.
So does the marker have an ID from which?
Yes. So the marker, so this is the important point. There are multiple snapshots in progress. First could be, each marker will have a unique ID. So a marker will tell you that, so if C is going to receive two markers. That we know, one from A and one from B. The first time you receive a marker, you say, okay, new snapshot, start recording. Second time you should recognize, so I already received a marker from C, I'm already recording. So this marker is going to tell me to stop recording, not to start recording. Yeah, so you can always distinguish whether it's the first marker or a subsequent marker.
Stop recording, but only from that particular node.
Stop recording that channel. So the marker is for a TCP connection and not for all channels. It's a per socket thing. So you stop recording more messages are being received on that socket. You may still record things that are coming from some other socket, okay, until you wait. Yes, question.
So why do processes save messages and not process them until they receive the next process?
Okay, question is why are processes recording and not, why are they saving and not processing? Okay, so there are 2 points. One is they are actually processing the message because think of this snapshot algorithm as working in addition to what the processes are already doing. This could be a set of web servers that are talking to one another. So each of these messages will be processed normally. Okay? What the snapshot algorithm is doing is, in addition, is saving a state of these processes on disk, because the reason we are doing this is a distributed snapshot. So if one process crashes, okay, what we will do is, rather than restarting the computation from scratch, we will ask each process to load the most recent snapshot, which is it will load the memory state that was saved to disk and it will compute from that point on. You will replay all these messages as if they actually came over the socket. Okay? So it is basically trying to start the computation from some intermediate state, not from scratch. So the messages that are going on disk are messages that are in transit. Okay, so basically those are messages that you should still process to be in consistent shape. Yes.
So new snapshots will replace the old one, like we don't reload if the new has been taken.
Yeah, so if you have multiple snapshots every so often, you can resume it from any snapshot. Okay, that prevents you from being rolled back to the very beginning. Clearly, the most recent snapshot allows you to resume from the most recent point of the computation. So you could throw away any intermediate ones, you could keep them. It is really, that's not my part of the algorithm. But the right thing to do is take the most recent snapshot that has completed. You can't take something that is partial. If you have a completed snapshot, you can safely throw away any older ones because that's the one you can resume from. Okay, any other questions here? Okay, so we'll go back to the question of why is this consistent. We still haven't answered that question. So remember what we want from a global state. We want to capture the local state of each process and the messages that have been sent but not received. These are called messages in transit. Okay. So we want every message that's somewhere in flight. Okay, because if you restart, that message is in flight. It's not going to be resent. It's already been sent. So you want to capture its state and replay it as if it was just sent again. Okay? So then you have to ask, is this algorithm capturing all the messages in transit? Okay? The messages in transit, you can see here, as I said last time, a message in transit is one that actually crosses that dotted line. Dotted line is when it intersects, that's where you actually received the marker message. So basically it has been sent, but it has not been received until the checkpoint. So it is in transit. Okay? Any message that is completely to the left has been sent or received before the checkpoint. Any message completely to the right of the dotted line has not been sent or received. So those are either completely processed or haven't yet been sent. So those are not messages in transit. The ones that are in transit are precisely a message like M3. Okay? So you should ask, what is a message in transit as far as this algorithm is concerned? A message in transit is basically a message that you have sent, okay, until, let's say all the messages that you sent until you receive the first marker that haven't yet been completely received and processed. Okay? So basically, if you take a snapshot at this point, any message before this point has been already sent. Of those messages, the messages that haven't yet been received are the messages in transit. Any message that was sent before and it's been received, we don't worry about. Okay? So now think about what is happening here. The first time you receive a marker, you basically take a checkpoint and send a marker saying anything after this you don't have to worry about. Worry about only messages before this point. Okay? Because anything after that is going to be a message like M2. So you send a marker at this point, okay, saying I've taken a snapshot. So only messages until this point could possibly be in transit. Okay, and of those subset, anything you already processed, don't even worry about that. So that's exactly what's happening. The first time you get a marker, you are going to checkpoint your state, send markers out, and then this process, if it has already checkpointed state, then between anything that has been sent after the first marker was sent, that says start recording, and between stop recording are the messages in transit. Okay, so if you think of, I start recording at this point, I stop recording at some other point, everything in between are messages that have been sent but not yet received. So those are the messages that you are actually recording here. Because this says start, some later point a stop comes, and these are all the messages that you have received in the on that socket. So those are the messages in transit. That's a somewhat intuitive, it's not a theoretical proof, but an intuitive explanation as to why this works. Okay, is that clear? So you really have to look at your sockets. So the point, the higher level point is the following. If you simply take a copy of your memory state and restart all the computation processes from memory state, you are going to lose messages. Okay, those are all messages that are in flight, will never get resent because they will get dropped by the OS. Your processes will start, some messages will disappear. Okay? So the first point is you have to capture not only local state, but also the state of your network. Okay, so in some sense, the messages in transit are the state of the network. The network has buffered some messages for. So those are the ones that you are capturing. Second is you only want to capture messages in transit. Okay, yes,
Is there a case where when A tries to send a marker to C, B reaches B's marker reaches first before A?
Okay. So question is there a scenario where A has started the checkpoint, it sent two markers, one to B and C. The marker from A to C, the channel, let's say the network from A to C is very slow. Okay? So the marker from A to B already reaches B. B sends the marker to C and that one reaches it first. That's your question?
Yes.
Okay. So that could well happen and it doesn't change what the algorithm is going to do.
So
What will happen in that case is if the marker has, from B is the first marker to be received by C, it will checkpoint its state. It will start recording on the incoming channel. And it will start send out markers on the outgoing channel. So eventually, so it will send this marker out. Eventually, the marker from A is going to come. Okay? And if there are any other messages in transit before it, here, they will get recorded as they would have anyway gotten recorded. Right? So I don't think it changes what the algorithm will produce. The
I was
speed.
thinking whether it will sort of create an inconsistent state.
No, so it should not create an inconsistent state because the marker is basically going to say what are messages sent before this point. How long the messages take to propagate doesn't matter. Anything that has already been sent has gone out. Okay.
So we are making an assumption that all nodes are equal. There is no master, no slave which. There is just a master which can initiate anyone.
So there is no master slave, there is no centralized control. Any process can initiate the algorithm, as is being said here. So any process can say it's been a while, let's take a checkpoint and then force everyone to take a checkpoint. So no central entity coordinating anything.
So as a process record the messages it sends after it sends a mark on a certain channel.
Okay, so the question is, does the process record mark messages it sends after it records? So you never record messages you send. You only record messages that are coming in. So if you sent it, it's not your job to record it because it's the other end's job to record whatever is in transit. Okay, so first of all, that's the important point is you only record received messages. Not you don't say I'm going to send this on a socket. Let me write a copy. It's not your job. You just send it. The other end is going to deal with is it a message in transit and should it record it or not. Okay, so that is never going to happen in any case. You never record sent messages. You record on the receive side, not on the sending side. Yes.
So for this to work, we clearly need TCP will be the underlying socket layer. Otherwise, it will not work because the messages could get reordered and you don't really have control as to when the market.
Okay. Good point. So point being made is you can. So I basically said you have unidirectional point-to-point channels that do not reorder messages. Okay, that's all you need. TCP is one protocol that's going to give it to you. So you cannot assume that messages are reordered. So you are fundamentally assuming messages are being received in the order which they are sent because if this marker hops over and over that message, then some message in transit will be missed. Okay. So you have to make an assumption that when you send messages in order A, B, C, D, they will be received in order A, B, C, D. It can take an arbitrary amount of time to be received. You are not making an assumption they have to be received in 1 millisecond or anything like that. But they will always be received in the order. Okay, so in order delivery is assumed. TCP is a protocol that gives you that. So we just assume channels are TCP. But any protocol that does that is good enough. Okay. Any other questions here? Okay, so I think that's a discussion on snapshots. We will move on. Okay, we will take that algorithm and tweak it a little bit and come up with a different algorithm called termination detection. Here we are not interested in recording the checkpoint of a process, but we are simply trying to figure out as the distributed computation finished. Okay, so you may ask, why is that even an important problem? What does it mean to say, has the application finished, and why do we need to come up with an algorithm to do that? Okay, so let's take a distributed simulation as a scenario. Okay, so there are multiple processes in this simulation. Each process is processing some data, it's sending messages back and forth, and at some point in time, maybe it feels it has processed all the data that it needs to process. Okay. And the question is, should it then just terminate or should it wait? Okay, so if there's nothing else for this process to do, then it should simply terminate. Okay. But how does the process know that there is nothing else for it to do? What if some other process decides to send new work to this process as part of the simulation? How will you figure out that is there anything left to do? Will somebody else send me any more work? Because I don't see anything to be done. All my request queue is empty. I've processed all the data. So am I done? Should I terminate myself, quit? Or should I wait thinking maybe some other process will send me some more work to be done as part of this computation or simulation? Okay. So how is the process to figure out locally whether when it feels like there is nothing, no new work arriving, should it terminate itself or wait because some more work may arrive? So we are assuming a scenario where it's not the user that decides, okay, I think things are finished, let me go and terminate them. We want the application processes to figure out when it is time to terminate themselves. Okay. So how do you figure out whether it's time to terminate yourself? Simplest thing is you ask other processes. Right? If you believe it, so you ask all the other processes, I'm done, are you done as well? If everybody says they're done, then you think, okay, there's nothing left to do. Everybody thinks they're done. They're simply trying to figure out if anybody else has any work to do. So if every process believes they're done, then the computation must be done. Right? But if any one of the process says, I am not yet done, I'm still computing, then you say if that process is still computing, it may generate some new messages as part of that computation. Those messages are requests that may trigger additional work. Think of a message being a request which requires processing to produce a response. Okay. So the basic point how we are going to do termination detection is the processes are going to query. Any process can start this. It will query all other processes. If all other processes says they are done, then you say everybody is done, time to quit and terminate the entire application. If any process says no, then you say no, you continue, because some processes are still computing. They may generate new work for the rest of the processes in the system. So you cannot terminate the system. Okay. So again, this is an algorithm that's going to run on top of the actual process of the application itself. So what we will do is we will have this algorithm, just as we had the distributed snapshot algorithm, we run as concurrently to the actual application. What the actual application is not important. It could be a simulation, it could be a client-server system, it could be a set of server processes, doesn't matter. Okay. So the way it is going to work is we will assume that again you can send messages to some subset of processes and they will send messages to other processes and so on. Okay, we will use this notion of a predecessor and a successor to decide who asked me first, are you done, and who else am I asking, are they done. Okay. And so that's basically what we will do. So the algorithm is very simple. Again, so we can think of this as something that's part of the distributed snapshot but adds an additional function to the distributed snapshot. The same thing is going to happen. A process can start off the computation termination detection algorithm saying, I am done, are you done? You send a marker message saying, are you done or not? Okay. When a process receives that marker message, okay, what it will do is it will send marker messages on its outgoing channel saying, I am done. If assuming it is done, it's going to send markers on all its outgoing channels saying, are you done or not? Okay. If it is itself computing, then it doesn't need to ask anyone else. Okay. It has veto power saying, I am not done, so the application cannot terminate. So it can immediately send a marker back saying, I am not done. Okay. So don't terminate yet. Okay. So the first time you receive a marker, you check your local state. If you are still computing, you know the application as a whole cannot be done. You just send back a marker back to your predecessor saying no, not done. Okay. Not done messages are called continue messages. Okay. And if you are actually done when you receive this marker, you will query your neighbor saying, I am done, are you done or not? So this will propagate. Eventually you will either get all done messages from all your neighbors, in which case you send a done back to your predecessor saying, I am done, everybody I have talked to is done, so I think our group is done. Okay. So you wait, or if anybody sends you continue, send a continue back. Okay. So you will aggregate all of these replies. Okay. If all the replies say done, then you say that everybody is done. If any one says continue, then you basically say the application cannot terminate. Okay. Is that clear? It's a simple way of querying. You could have basically just sent a broadcast query. Okay, you ask all n-1 processes, they all reply, and you could have gotten that answer in one shot. Here you don't do that. You basically send messages only to your neighbors with which you have active TCP connection, and only ask them, they ask their neighbors, you collect responses and send responses back. Okay, is that clear? It's a very straightforward algorithm. It looks like the snapshot algorithm solves a slightly different problem, okay, called termination detection. So that's what we will say about termination detection. We'll move on to the next problem, which is actually an interesting one, something you may use in your subsequent labs as well. And this problem is called election algorithm, or also referred to as leader election. Okay. So let me describe what the algorithms do, and then we'll see how the algorithms work. So let's assume you have a distributed application of some sort. Okay. In this application, you want to have one node take on some additional responsibility. Okay. And you want the application as itself to decide what that node is going to be. In other words, you want the processes to elect a leader process. Okay? And then once that leader process is elected, it takes on some responsibility. What that responsibility is depends on the application. Okay? In Skype, if you remember, when I talked about Skype and peer-to-peer system, I said you can elect a super peer, a super node that's going to basically maintain the directory of who is logged in, who is not logged in on behalf of a set of nodes. Okay? So in that case, who becomes the super peer could be an election algorithm. It's not statically determined by the application developer. In your code, you don't say process 10 always becomes the leader. You basically run a leader election algorithm and then you elect a leader on the fly. Okay? So now if that leader crashes or something happens to it, you can start a new election algorithm. And among the remaining process, you elect another leader. And that leader takes on the responsibility of whatever the old leader was doing. So in many different applications, there is this notion of having one process take on some role on behalf of the application or other processes, but which process is chosen to take on that role is decided dynamically at runtime. And that is often done through what is referred to as leader election algorithms, or simply election algorithms. Okay? Now we want this to be done in a distributed fashion. Okay, so but we'll start with a centralized algorithm, then we'll see how to do this in a distributed way. Okay, we'll see a set of algorithms. Is the problem clear first? Okay. So distributed algorithms need one process to act as the coordinator. Okay, so we'll call this leader also as the coordinator as far as the application is concerned. So you need to pick one coordinator. It doesn't matter which one is the coordinator. Okay. So in our clock synchronization algorithm, the time server was the coordinator for the synchronization. You can assume that if you want to pick that process dynamically, you run a leader election and some process becomes the time server or some machine becomes a time server in the system, as an example. Okay, but there will be other places where we need coordinator. Okay, so we need to pick a unique coordinator and we need to find out a way to pick a new one whenever the algorithm or the leader fails. Okay, so we'll start with a simple algorithm called the bully algorithm. So the algorithm is actually very straightforward. So we will assume every process has a numeric ID, okay, which is unique in the system. For simplicity, we'll just assume they are numbered 1 through 8, but it doesn't matter what the IDs are. Just assume every process has an ID associated with it, and process IDs are unique in the system. Now the process ID doesn't have to be the OS assigned process ID, it could be any number. Okay. So here we'll just assume that processes are numbered 1 through 8. And our leader election algorithm is always going to pick the highest numbered process that is currently alive to be the leader. Okay, so of all the processes that are up, we are simply going to pick the highest ID process and say that is going to be the leader. And the question is, how do you figure out of the processes that are there, which is the highest ID process that is still currently running? Okay, that is what the bully algorithm is going to do. Okay, algorithm is actually, once you understand, is very straightforward. There are only 3 messages that will go out in this protocol. One is called an election algorithm, rather election message. There's an OK message and there's an I1 message. Okay, you can imagine what they do based on the names, but I'm going to describe what the algorithm is first. Okay. Any process P can start an election. So let's say some random process is trying to contact its current coordinator is not responding, process thinks coordinator has gone down, time to start a new coordinator, so you start an election. Okay? So any process can start the election. You can actually have multiple elections in progress. At the moment we'll assume there's only one, but you can have more than one, it will produce the same result. Okay? So the way you start this is process sends election messages to all processes with IDs greater than it. So if you are process 5, there are 8 processes in the system. You will send messages to process 6, 7, any process that has an ID higher than you. Okay? And that's an election message. Okay? Now, if a process receives an election message, okay, clearly it has an ID higher than the one that sent it that message, because you are always sending messages to processes with higher numbered IDs. Okay? So then you tell the process, send a reply back saying, OK. OK just says that I am alive. It's sort of a heartbeat message saying I am alive. So you don't need to become the coordinator. It will be either me or all processes higher than. Okay? That's what OK means. OK basically tells that process P that started the election saying somebody with a process ID higher than me is actually up at this point in time. So P, now it's no longer P's job to figure out who the coordinator is going to be. And then what happens is each process that received the election message will recursively start election messages. Okay. So lower ID processes drop out because as soon as you receive the OK, you say, OK, I'm not going to worry about this, somebody else's job. So you guys start your own election and figure out. So each process with ID lower than a higher ID process successively drops out. And then the remaining processes keep running elections until there's only one process left. At that point, it basically has no other ID process higher with ID higher than it. It declares itself to be the leader and it sends an I1 message to everyone saying, I'm the new leader. Yeah, there's a picture here that shows you exactly what's going on. So here you will see that there are 8 processes numbered 0 through 7. Okay. 7 was the coordinator, but it crashed. Okay. At some point in time, 4 is going to detect that the coordinator is not responding. It starts an election. Okay. So it's going to send election messages to 5, 6, 7. 7 is crashed, so it's not replying, so it's not going to do anything. Okay. So 5 and 6 are still running clearly. Okay. So what 5 and 6 will do is they will both send OK messages back to 4 saying we are both up. Okay. Now we'll figure this out. Okay. So 4 drops out. 4 basically says there's nothing for me to do. Somebody else will now deal with this. Okay. So 5 is going to start an election. 6 is going to start its own election. So 5 will send a message to 6 and 7. 6 will send a message to 7. Okay. So you see now there are two. That election triggered 2 other elections. One starting from 5, one from 6. Right? When 5 sends a message to 6, 6 is going to send OK back to 5. Okay? So then 5 drops out. 6 has already started an election and it sent a message to 7. 7 doesn't respond. Okay? So then 6 is going to say there is no process that's higher than me that's replying to my election request. So I declare myself to be the coordinator. Okay? So then 6 sends I1 or a coordinator message to everyone saying I'm the new coordinator. So now all processes know who the new coordinator is. Okay, 6 has been elected the new coordinator. Is that clear? Very simple. So the reason it's called bully algorithm is higher ID processes bully the lower ones to drop out. Okay, and they basically try to become the leader. Any questions about this? Okay. So now the thing to keep in mind is processes can crash during an election, in which case you can always start new elections. Okay. But so long as while the election is actually taking place, no process crashes, it will produce the right result for you. Okay, is that clear? Because in this case, what may happen is after 6 sent a message to 5, 5 has dropped out, 6 is the only one left. Okay. Technically, it should send now I1 message to everyone declaring itself to be the leader, but 6 could crash before it sent out and became the new leader. If that happens, then what is going to happen is there will be 4 would have started that election. It's not heard for a long time. It was bullied and asked to drop out, so it didn't hear. So now either it or someone else will say there is nothing happening. I can't reach the coordinate. Let's start a new election. Okay, so you start another election. At some point, this process will converge because if processes keep crashing, then no one will be left. So there's no leader to elect. But if there are some processes that are stable and no other processes are crashing, election will result in a stable reply and then you will have a leader. But there may be a period of time when processes are going up and down when your leader election may not produce a result. Okay, so that's something to keep in mind. And that's okay because eventually we want one and that will actually happen. Okay. The reverse is also going to be true if now 7 comes back up after a while. Okay. And it basically sees that there is, before it crashed, it was the leader. Okay, now it has been rebooted or something like that, and so it is restarted. So it is free to start an election. So any process can initiate an election. So if 7 comes back up, it will start an election. There's nothing higher than it to send. So it will declare itself to be the leader, and bully 6 to drop out. So it will basically take over. And that's also fine. Okay, leader doesn't have to crash in order for a new leader to be elected. A leader, if some higher ID process tells you to drop out, you say, okay, you can be the leader. That's the rule. Yeah. Okay, so you can be told to stop being the leader, or you can crash and a new leader is elected. Yes, question.
So after 6 has taken over as a coordinator,
Yeah.
Suddenly 5 becomes more utilized than 6.
Yes.
You say that 5 can randomly start, but I mean
7.
5.
Okay, so repeat your question. So after 6 becomes the leader, 6 5 has a heavier load. Okay.
Yeah, and then 5 suddenly gets a heavier load compared to 6.
Okay.
So how does it know that it has a heavier load and it has to trigger an election right away? Or is that even necessary? Is there a scenario where one of the child nodes that is can have a higher number of
Okay, so you are asking a good question, which is that if some processes have higher load, should some other processes take over the responsibility of being the leader? Right? So in this algorithm, this is a very simple algorithm. You're simply electing the highest ID process to be the leader, irrespective of the characteristic of that machine. Maybe the machine doesn't have good network connectivity. So as a coordinator, it has to exchange a lot of messages. We didn't take that into account. Maybe the machine is already overloaded. Okay? Yet we made it the leader. There may be other processes that may have much lighter load, may have much better connectivity, could have been much better leaders. But this algorithm is unaware of any of those characteristics. It's simply electing the highest ID process. We'll see some other algorithm that will elect leaders not based on their IDs, but rather based on their current load or connectivity and so on. Okay, so there is a whole spectrum of leader election algorithms you will see in the literature. Okay, they will do different things depending on what kind of leader you want. A well-connected leader, a leader with lots of idle processes, so coordinated task may be heavy burden on that machine. Okay, so you don't want an overloaded machine to also become the leader and become even more overloaded. This algorithm doesn't do it. It's simply saying processes have ID, we just make the process with the highest ID a leader. Okay. Any other questions? Okay, so next algorithm for leader election is ring based, also fairly straightforward. So what happens here again is processes have unique IDs, okay, numerical IDs, and in this case we assume that they are arranged in a ring topology. Okay? That doesn't have to be a real ring. All that means is, as far as leader election is concerned, process I, okay, will only exchange messages with process I minus 1 and I plus 1, or the process with the immediately lower ID that's still alive and the immediately higher ID that's still alive. Okay. For the normal application, any process can talk to any other process. Only for leader election, we assume that in this case, just to reduce the number of messages, because in the previous case we have order n square messages. We'll come back to complexity in just a moment. So to reduce the message overhead, we will limit the messages that are being exchanged for leader election, not for the actual application itself, to be exchanged with only the processes below and above in terms of numerical ID. Okay. So what happens in this case is, again, any process can start an election message, and the way this is going to work is you basically start an election message by sending an election message to the next node that has the ID above you, saying, I want to start an election. Okay. And so this election message is going to circulate through this logical ring, and as each node receives the election message, it's going to simply attach its ID, saying, I received the election message, I'm process 10. Process 11 is, I received the election message, I'm process 11. And so this message is going to circulate through this logical ring and come back to the process that started it. And then in that election message that has circulated through the ring has come back, you have a list of all the ID of processes that are up and running. So every process has just simply appended its ID to the election message and sent it forward. Okay, so it's just going to circulate and come back. So now you have a list of all the ID processes that are alive. You just pick the max of those and say this is the process that has the highest ID. So this is the one that's going to be the leader. Yes, so here is, I think there's a picture here. So in this case, the picture is showing that two processes realized 7 had gone down and they started independent elections, which is the more complex case. So 2 has started an election, 5 has started an election. Both, if there are no more crashes, both will yield the same leader in the end. Okay? But for simplicity, we'll just take one of those election messages. So 5 starts an election, it puts his ID, sends it to 6. Okay? 6, since 7 is crashing, 6 is going to append its ID, send it on, will send it to 0, 0 will send it to 1, and so on, it will come back. So that when it comes back, 5 will determine that 6 is the process with the highest ID that's still up and running. It declares itself. Okay? This other election that was started by 2, because you could, any process can start an election, and same thing will happen. This election message will circulate through this logical ring. Okay, it will come back, and 2 will also see that 6 is the leader. Okay, so both will be in the same result in this case. Okay. So this is a simple ring-based algorithm. You will see that this has order n message overhead because there is basically first cycle you will basically send an election message, collect all the IDs of processes that are alive, then you send another message declaring the results of the election. You will say 5 will say 6 is the new leader, and that will circulate, everybody will get to know the new leader. So there will be two cycles of messages, so 2n minus 1 messages will go to n minus 1 because one process is crashed. Okay, but still order n overhead. Okay. In our Bully algorithm, you have order n squared, because the worst case is when the process with the lowest ID, which is 0, starts the election. It sends n minus 1 messages. Okay, that triggers n minus 1 election each. So then 1 will start, it will send n minus 2 messages, and then 2 will start, it will send n minus 3 messages. And so you will have n minus 1 plus n minus 2 plus n minus 3 and so on, which is order n squared. Okay. So this will achieve the same result with much lower overhead. Okay, this is referred to as the ring algorithm for leader election. So I already talked about complexity in ring. It is 2n minus 1 messages always. Okay, in this case, worst case is n square messages. Best case is the highest ordered process decides that there is the actual leader has crashed. It starts an election. There's no one else to send the message to, it declares itself a leader. Okay. So that's only going to trigger n minus 2 messages. Okay, but it sends messages to the rest. Okay, so this will have a overhead somewhere in between. Okay, that's the worst case, that's the best case. Okay, this one is going to have constant overhead, not constant, but on, but 2n minus 1 messages always. Okay, so its message overhead is always going to be that. Any questions on leader election? So we'll see several different scenarios now. So those are two very basic ones. This has been a rich area of research. We'll literally see dozens and dozens of papers on leader election which take different scenarios. And the way they all differ is in neither of these algorithms did we look at the node's characteristics. Okay. In most applications, you want a leader to be somehow a better equipped machine or a better equipped process or a better machine with a better network connectivity or some such characteristics. So you will basically probe to find those machines rather than just the machine with the highest ID. In our elections, we were probing for the process with the highest ID. So now you want to change the metric. You don't want the process with the highest ID, but least loaded process. Okay? So you can immediately think of the ring algorithm and say, instead of asking for process ID, let's start an election and ask everyone to append their load. Okay? So the message comes back, you now have the load of every machine in the system. You can pick the least loaded one and make that the leader. Okay? Or you can say, fine, tell me your available network bandwidth. Okay? So you probe for that and then messages come back, you find the one with the most available bandwidth. You can find any metric you want. Okay, ID is just a metric that we just picked up as a randomly chosen metric. It's one that makes it simple, but other metrics can apply. Okay, so that's basically going to lead to an entire spectrum of algorithms. Here is one that is run in a sort of more wireless environment, which is probing for a leader with the best wireless channel characteristics to be the leader. So here you will see what has happened is, so each process, well, not the wireless characteristic, but the processing capacity. So numbers on nodes are not their IDs, but how many cycles they have. Okay, what is the capacity they have that can be used to perform the coordinated task. So you are going to do a broadcast, which is the same. You are going to send these messages as a broadcast. They will propagate through the wireless network. You will collect the channel node capacities and decide who is the leader. Okay, as an example of what we just talked about. Okay, so I'm going to go into the details of it. It's basically how it is done is not as important as you want to probe all the or query every node somehow, get all the responses back, pick the metric that you care about, and find the leader that has the best metric. Okay, so that's really how it works. So this slide is simply showing you what I was talking about in Skype. In Skype, the super peers are actually elected through leader election. It's a dynamic process. Okay, because the code doesn't say if this machine comes up, it becomes a leader. In Skype, people can log in and log out. Okay, so if you are actually on a good machine and your machine has lots of CPU cycles and good network, your Skype process may suddenly become the leader for a group of processes, completely transparent to the end user. Okay, if you actually look at network characteristics, you will see that although you are not on an active Skype call, your Skype process is sending and receiving lots of requests. Okay, that's the reason, because it's become a leader. So it's trying to do something on behalf of the entire Skype network that's local. Okay. So in this case, the way it is done is you will find nodes. So first of all, you want low latency access to other nodes. You want super peers to be evenly distributed. Okay. You don't want to have a bunch of super peers that are all clustered, because this is Skype is a global network, a global application. You want the super peers to be in all states, all countries, all continents. So you may have one for every geographic region. You want to run a leader election and find a leader there. Okay. So you want them to be evenly distributed. You want them to be a certain fraction of the nodes, because any user can terminate their Skype application at any time. Okay. So you cannot assume if you chose a leader, the leader is going to be a long-running Skype session. If you just kill the process, then you have to pick a new leader, and it has to do extra work to reconstruct the state that the previous leader had. Okay. So what you do is you basically have some redundancy. Okay. So you can have multiple peers that have the same state. So if you log into Skype, not only a local super peer, but some other peers also know your login. So if this peer goes away, the other peer knows your state. Okay. So you do that, and then you basically say that the super peer should not serve more than a certain number of nodes, okay, because that is going to annoy the users. If you have a good machine that's connected to a gigabit Ethernet, okay, and then your super peer starts doing a lot of work and creates a load on your machine, you will not be happy. So you're not using Skype, it's using 100% of the CPU cycles by doing this work. So you basically limit the number of nodes a super peer manages so that it is transparent. Users don't worry about this, don't bother if there is a little bit of extra traffic and so on. Okay, so you want to now use all of these metrics to decide who gets to be a super peer, how many peers do you have in the network, how do you have some redundancy, because it's not one leader, as you can imagine. Each super peer is a leader for its group, okay, and then groups may have some overlap. So the leader election that algorithm used here is going to be somewhat more complex than what we studied. But nevertheless, you will use this metric and decide dynamically. Okay, you can vote or you can query nodes and figure out who becomes a leader. Okay. As an example of a real application that uses, there are many applications that use leader election. Okay, so it's a very common problem in many distributed applications. Skype being just one of them. Okay, is that clear? Okay, so I won't have much else to say here about leader election. If there are no other questions, I will move on to the next problem, okay, which is going to be distributed locks, or distributed synchronization. So here is where we are now going to start building up. Okay, so we have done the base level things. We studied clock synchronization, we studied vector clocks, we studied leader election. You'll see that in distributed synchronization, we are going to use some of these and start solving higher level problems. So first, the problem should be clear. Okay, so we have a set of applications, set of processes that are part of a distributed application that need to get a lock on some data structure. Okay. Now, if this was a centralized application, a multi-threaded application, the lock would be internal to that process. Okay? But these are applications on random machines. Okay, there's a, let's say, and then they want to grab a lock on some object, maybe it's a file on some other machine. Okay? How do you implement this notion of a distributed lock so that only one of these processes gets access to that shared resource? Okay, just as you have a centralized lock. Okay, so in other words, how do you implement a lock? I presume all of you know what a lock is. How do you implement a lock when processes that are trying to grab the lock are spread across on arbitrary machines? Right? How do they all coordinate and figure out who gets the lock, who has to block, when the lock is released, who gets to go next and grab the lock and so on. Okay? So that's really the question that we, so and the same is true whether you want to implement a semaphore lock or a monitor. What is it that you are implementing is not as important as how the processes are going to coordinate. Okay? So how do you do this for multiple processes? Processes may be running on different machines. So we want to be now making a distributed lock. So we'll start with a centralized version, okay, of a distributed lock, and then we'll see decentralized implementations. Okay, so now you'll see how we build up on everything. So we'll assume processes are numbered. Okay. We will assume that one process is chosen as the coordinator. Okay, so the first thing is you are going to learn leader election and elect a leader. That leader is the lock coordinator. For every lock you want to manage, you pick one leader. So you are responsible for determining the state of the lock. Who has the lock? Okay, how many processes are queued up to get the lock is the task of the coordinator. Okay, so first thing you run a leader election. Pick a coordinator for the lock. So now what you do is every process that needs to grab a lock needs to first send a lock message to the coordinator. So you do lock acquire, but lock acquire is a message, a network message that goes to the coordinator that says, I am process 10, I need to grab the lock. And the coordinator is now going to implement synchronization. It will basically let one process grab the lock at any given time. So if a process sends it an acquire message, the lock is free, the coordinator says, go ahead, you have the lock. And it marks the lock state to be in use. If subsequent requests come in, they are all queued up until the lock is released. And once the lock is released, the next process gets to go next and so on. Yeah. So that's shown here. So a centralized algorithm. Yeah. Coordinator is needed. Coordinator is the central point that's going to determine who gets the lock. So 4 processes here. 3 is chosen the coordinator. Okay. And so what it does is it has a queue that tracks who is requested the lock and so on. First time you get a request, okay, you are going to basically give the lock. Any subsequent request is queued up. Okay. So in this case, 1 made the first request, it got the lock. Okay. 2 made a request, it was queued up. So you have to block. Lock is in use. When 1 released that lock, then you will look at your queue and say who is queued up, and you will say 2 is requested the lock, go ahead. Okay. So you are going to have a central point that is going to manage the lock. This question.
So if the coordinator needs to grab the lock, does it have the option of preempting and grabbing the lock, or should it queue itself?
Okay. So question is the coordinator needs to grab the lock. Should it preempt the lock or not? So locks are not preempted. The coordinator is also a normal process in the system. So it will send a message to itself. Okay. So think of this as the coordinator has think of it as 2 threads. Thread 1 does the normal application processing. Thread 2 does lock processing. Okay, and so in this case, the normal application that's running on 3 will send a message to the coordinator that's also running on 3 saying, I want the lock. And it will be treated no differently from any other process. If the lock is available, it will get it. If not, it will be queued up. So that's the way it will be. You don't get any special treatment to get the lock just because you are a coordinator. Okay, everybody does the same thing.
The resource need not be at the leader, right? The resource can be saved somewhere else.
Yes.
So is there does the protocol specify any interaction between the leader and the place where the resource is so that there is no ambiguity?
Okay.
Like the local process can access it or something?
Yeah. So question is, what is the resource that you are putting a lock on is independent from the coordinator that's managing a lock for that resource. Resource could be at a file. File could be on one of these machines, it could be on some other machines, we have not specified that. Okay? And then there is a coordinator that's independent of the resource. Okay? Now again, as you rightly point out, it would be helpful if the coordinator was at least on the same machine as the resource. Here we said you pick the metric is you pick the highest order process as the lock coordinator. Okay, but that's an abstract metric. So you can always make this better by saying I put the coordinator on the same machine as the resource, so I can actually look at the resource and do better coordination. Here the coordination is completely independent from where the resource resides. Okay, you did ask a question, if some local process tries to access it, the assumption is whether the resource is local to you or not. If it's a shared resource, you have to get a lock. If you don't get a lock on a shared resource, then synchronization obviously is not going to work. Okay, so every entity in the system knows that the resource is shared, whether the resource is a file on your machine, file on some other machine. So the assumption is you will actually get a lock by talking to the coordinator, and you are part of the system. That's the assumption we have made. But you are right that the technique can be bettered by simply putting the coordinator on the machines with resources that are being protected. Here we are not doing anything like that. It's an abstract protocol that simply says you elect a coordinator, coordinator tracks the state of the locks and grants locks in some order. Okay, so now here are some properties of the algorithm. It simulates a centralized lock by making blocking calls. Okay, so think of lock acquire is now a remote procedure call or a remote method invocation, RMI call. Okay, so you go to send it to the process. If it's queued up, then you won't get a reply to your RMI. Your RMI is queued up for a long period of time. So lock acquire will block like just as if you have done a lock acquire on a local lock. Okay, so it looks from other processes standpoint, although the lock is distributed, it looks the same as actually getting a local lock. These are blocking calls that are made. If the lock is available, your RPC or RMI will return back to you, so you know you have the lock. That's the way it will work. So from an implementation standpoint, it looks exactly the same in terms of usage as centralized. Okay, it is fair because all you're doing is you're queuing requests in the order in which they were received, and you're granting locks in the order in which they're received. You're not favoring any one over the other. So fairness is a property of the technique. It is very straightforward in that grabbing a lock requires exactly 3 messages and releasing it. The first request message, a grant message that says you got the lock, okay, and a release message. Okay, if this was done as RMIs, there will be only 2 calls. A lock acquire that makes the first RMI call, a lock release that releases. Okay, and then replies to that. Okay, those are all advantages. Disadvantages is it's a centralized algorithm. There is a coordinator. Okay, coordinators can fail, processes can fail. So you can say if the process failed, let's elect a new coordinator. Okay, that's good, but the new coordinator needs to know what is the current state of the lock. If it doesn't know that, you have a problem, because if the lock is in use, a new coordinator is elected that gives the lock to some other process, then you have a problem. Okay, because you will not know, you can't have 2 processes holding the lock at the same time. This is mutual exclusion. So you not only need to detect a dead coordinator, you need to figure out what is the state of the lock that the dead coordinator put it in before it crashed. Okay, so that's going to be a problem in any centralized algorithm. Okay, so, and you can't actually have any ambiguity there. A lock can only be held by one process at a time. And if you violate that, then you don't have a locking protocol. Okay, that's not going to give you mutual exclusion. The other problem is how do you even detect if you only had those 3 messages going back and forth? You cannot even detect a dead coordinator from the lock being in use. Okay, you send the initial request message. Okay, you haven't heard back from the coordinator. What should you infer? The coordinator is down, so it's not replying to you, or some other process is holding the lock for a long period of time. Okay, either of those 2 scenarios could be true. You can't distinguish between them. So it is hard to detect, just using these 3 messages, hard to detect a dead coordinator. Clearly you can augment the protocol by sending what are referred to as heartbeat messages to the coordinator saying, I sent an require message, it's been 5 minutes, I haven't heard back, are you still alive? Okay, then you can send a heartbeat message, the reply will come back, yes, I'm up. So then you know that it's the lock is in use, not the coordinator disappeared and you are not getting a reply. Okay. So to detect a coordinator using this protocol itself is hard, a dead coordinator, but you can easily augment it, which is what is often done. Okay, so those are the disadvantages of a centralized locking algorithm. We will look at two decentralized or distributed locking algorithms. The first one is basically going to be something that uses the notion of voting. Okay? So what happens in this case is you assume that every process in the system, okay, does the same job as what the coordinator would do, which means when you send a message saying I want the lock, everybody gets to say yes or no, just as the coordinator would have said yes or no. Okay. So in other words, when you send a message, you get back a reply saying yes, you can have the lock, or no, you cannot have the lock. Okay. And you use voting. Basically, if the majority of the processes in the system say you can have the lock, then you go ahead and get the lock. You can't have two different majorities saying you can have the lock to two different processes, because if you have two majorities, there are some processes that are at the intersection of those two majorities. They have said yes to two processes. That's faulty. Okay? So you can have only, if a majority reply to you, you know that is safe, because if some other process asks for the same lock, it cannot also get the majority. It has to only get a minority. If it also got a majority reply yes, then that means that something is wrong with your protocol. Okay, there will be at least one process that said yes to two machines, or two different requests. Okay, so you can simply use voting, which says I use strict majority, and if strict majority say yes, then I can simply go ahead. Okay, if the majority said no, then I just block. Okay, and then somebody is going to tell me later on that I have the lock. Okay, that's a way to make it distributed and deal with failures. In this case, so basically what happens is everybody gets to weigh in on whether the lock is in use or not. Okay, and I'm going to talk about a very specific protocol to do this, but is the idea clear as to how this is going to work? Yes? No? Okay. Okay, so the distributed algorithm is as follows. It's also referred to as Ricard and Agarwal's algorithm. Okay, and it is actually going to use now notion of Lamport's clocks to implement locks in a decentralized fashion. So this is why I said we are going to keep building. Okay? This doesn't use leader election, but it uses Lamport's clock. So Lamport's clocks are going to figure out who made the first request for a lock. We are going to use the happened before relationship to say if two messages came in saying get me a lock, which one was sent first. So from a fairness perspective, the first process that makes a request should get the lock first. And we are going to use Lamport's clock to decide on ordering of who makes requests in what order. And that's the reason we want Lamport's clock. Otherwise, it doesn't matter. All you need to do is ensure that one and only one process gets the lock. Okay, for fairness perspective, if you want to grant locks in order, we are going to use Lamport's or metric clocks can also be used to decide if concurrent locking acquire request came in, who made it first, who gets to go first. Okay, that's the basic algorithm. So we will, if we use Lamport's clocks to do this, we will use the variant of Lamport's clock that implements multicasting and gets total ordering. Okay? Just the basic Lamport's clock algorithm is not enough because it only gives you partial ordering. So you have two messages come in, those two processes never exchange messages. If those are concurrent events, I can't decide who gets the lock. So I need total ordering. Okay, so we will assume there's, I mentioned that variant last time, that you will, if you multicast every message to everyone else, you can get total ordering. You either do that or you simply use vector clocks. Then there is no problem either. Okay. So the way it will work is any process K will enter a critical section as follows. It will increment its current Lamport's clock. Okay. It will send a request saying I am process K, I need the lock, this is my current Lamport's clock timestamp. Okay, so you'll send that to all n-1. This is decentralized algorithm, no coordinator. So you send it to all the remaining processes. Okay. Then you will wait until every other process has sent you a reply. Reply basically says go ahead. You have to wait until everyone tells you go ahead. Not a majority. In this case, everybody else has to tell you go ahead. And once everyone else says go ahead, you know it's safe. You asked everyone, I'm going to get the lock. Everyone else said go ahead. So they must not need the lock. So I'm the only one that needs the lock. So I get to go ahead. Okay. Now, you will not get a reply from every process immediately. Specifically, any other process that is trying to either hold the lock or grab the lock may delay sending the reply. So the way replies are sent are as follows. If you are a process that receives a request message, you do the following. You send a reply immediately if you are not at all interested in the lock, saying go ahead, I don't need the lock, I'm not going to need the lock. Okay? If I already hold the lock, then I simply wait until I'm done and then send a reply. Okay? Because if I already hold it, I can't say go ahead, I hold the lock. So I wait until I'm done. When I release the lock, at that point I send a reply because I am done at that point, some other process can go ahead. So those two are straightforward cases. The most interesting case occurs when I receive a request message from some process. I'm a process that's also contending for the lock at the same time. Okay? So in this case, what you do is you compare your timestamp from when you requested the lock to the timestamp of this other process and say which of us actually sent the request first, because I also sent out the request message. That process sent a request message and I received its request message. So I look at the timestamp, say which of these two happened first. Okay, because we are trying to get a total ordering based on the timestamp or the vector, you should say one event happened before the other event, and the process that made the first request is going to win in this case. Okay, so if my timestamp is lower, I am going to hold back, saying I am going to win, so I will send my reply after I release the lock. If that process's timestamp is lower, I have to yield to that process and say, okay, you go first and then you tell me when you're done and I will go next. So we are using timestamps here where processes order themselves and decide who gets to go next. Okay, is that clear? So fully distributed algorithm, no central point, no coordinator. We are simply using Lamport's clocks and well-behaved processes that are gracious enough to yield to other processes. Say you made the request, so please go ahead, and then they will tell you when it's your turn. And that's the way it will. Yes.
What if a particular process is down and that's the reason why it doesn't send a response?
Okay, so we'll come back to, so I'm not going to talk about this. So fully decentralized algorithm, okay, but now you have n points of failure. You have to receive reply messages from every other process before you can make progress. If any process crashes, okay, and you don't receive a reply message from that, you will not be able to distinguish is that process not replying to you because it is holding the lock or contending for it, or it has gone down. Okay? So this is a rare case. This is doesn't happen very often. This is a rare case where your distributed algorithm has worse failure property than a centralized algorithm. In a centralized algorithm, there's one coordinator. Okay, it was a single point of failure, but you could have done something, elected a new one. Here there are n points of failure. If any process crashes, nobody can make progress. In that case, if the coordinator crashed, you couldn't make progress. But if some other random process crashed, maybe the rest of them could still get locks and make some progress. Okay? So we should tell you that distributed or decentralized algorithms are not always better than centralized algorithms. That's a general rule of thumb. Okay? Here's a scenario that's a counter example. You actually you thought you were doing something smarter and better, but you made it actually worse in the process. Okay? So n points of failures. Furthermore, all processes are involved in all decisions. Whether I want the lock or not, I keep getting these request messages. I have to keep sending reply messages. I have to incur that processing overhead. The centralized one, only the coordinator incurred that overhead. Okay? So a lot more processing at all of the processes that are part of the system. Yes, question.
That's a reflection of the bad protocol design, not really the distributed aspect of it.
So I agree. So this is a specific scenario with respect to the algorithm itself. It has nothing to do with, not a blanket statement saying all distributed systems are worse than centralized systems, and there will be no need for the course itself. But this is just a protocol issue. But the point is that when you make something distributed, you shouldn't assume that you made it better. You have to think about it. You actually make it better. Okay, so that's what you need to keep in mind. Okay, so we are going to few minutes early, but you are welcome to be here. So let's stop here. There's one more algorithm which is also decentralized that uses token rings to do locking. We'll talk about that next time because we ran out of time. So we'll stop here for today. Okay, as I said, next week spring break, no classes, but I will try to put out the next lab before spring break so people can get an early start on the lab. Should you have time for doing something. Otherwise, have a good spring break. I'll see you a week after next.